Hello viewers, in today's session we are going to discuss some important problems related to the famous Euler's theorem on homogeneous functions in partial differentiation. Right? So in this class we'll solve some important problems based on Euler's theorem. But before solving the problems, let us quickly see the concept of homogeneous functions and the statement of Euler's theorem on homogeneous functions. So now to understand the concept of homogeneous functions, let us consider these four examples. So in the first one, we have the function that is in two variables, x and y. So we have x comma y is equal to x square plus y square plus 5xy. Right, and here we can see that the degree of each term is 2. Here we have 2, here we have 2, and here also we have 2, because here we have x raised to 1 and here also we have y raised to 1. So the degree is 1 plus 1 2. Right, so let us take here x square common from these three terms. So we can now write x square, and here we have 1, and then we have y square over x square, and here we have simply 5y, and here we have simply x. Right, so taking x square common from these three terms, we have this expression. Right, so now we can further write x square, and here we have 1 plus y over x square, and here we have 5 times y over x. Right, so let us now see this expression. Now this is a function of y over x, and here we have x square. So if we denote this expression by f of y over x, then we can write x square times f of y over x. Right, so now our function small f of x comma y is equal to x square times capital F of y over x. So any function which is of this type, that is x f of x comma y is equal to, say, x raised to n, and here we have f of y over x, then such a function is known as a homogeneous function of degree n. Right, so this function f of x comma y is a homogeneous function of degree 2, because here we have x square. Right, so we have expressed this function like this. So this is a homogeneous function of degree 2. So now let us try to express this function in this form. Right, so what we will do, we have f of x comma y, and here also we have three terms, x cube plus y cube plus 3x square y, and we can easily see that the degree of each term is 3. Here we have 3, here we have 3, and here we have 2, and here we have 1. So 2 plus 1 is 3. So let us take x cube common from these three terms. So we have x cube, then we have 1 plus y cube over x cube plus 3 times y over x. So let us write x cube, and here we have 1 plus y over x cube, and this is 3 times y over x. Right, so now this expression is again a function of y over x. So we can now write x cube and f of y over x. So this function, that is f of x comma y, is now expressed like this. And if we compare these two expressions, then we can see that the value of n is 3, that is the degree of this function a homogeneous function is 3. So this is also a homogeneous function, and the degree is n is equal to 3. Now let us consider the third example. So here we have f of x comma y is equal to x cube plus y cube divided by x plus y. So here in order to express this function in this form, in the numerator we will take x cube common. So we have 1 plus y cube over x cube, and in the denominator we can take x common, and we have 1 plus y over x. So now here we have x cube and here we have x raised to 1. So here using the laws of exponents, we have x raised to 3 minus 1, and then we have 1 plus y over x cube, and here we have 1 plus y over x. So now this function, this is a function of f of y over x, and here we have x raised to 3 minus 1, that is simply x square, and here this expression can be denoted by capital F of y over x, right? So we have expressed this function f of x comma y like this, and we can see that the value of n is 2. So this function is also a homogeneous function of degree 2. So here we have n is equal to 2. Now let us consider the fourth example. So here we can write f of x comma y, and in the numerator we have root x minus root y divided by, in the denominator we have x plus y. So in the numerator we can take square root of x common. So we have 1 minus square root of y over square root of x divided by, here we can take x common. So we have x 1 plus y over x. So let us further rewrite this expression as x raised to half. This is root x, so x raised to half, and in the denominator here we have x raised to 1, and then we can write 1 minus y over x raised to half, and here we have 1 plus y over x, right? So now here again using the laws of exponent, we have x raised to half minus 1. So we have x raised to minus half, right? And here this entire expression is a function of y over x, so we can write f of y over x. So we have f of x comma y as x raised to minus half f of y over x. So this is again a homogeneous function of degree minus half. So here the value of n is equal to minus 1 over 2. Now let us quickly see three more examples. So here the fifth one is f of xy is equal to x cube y times e raised to y square over x square. So we can now write this function f of x comma y as x raised to 4, and then here we can write y over x. Here we have x cube y, and here we can multiply and divide by x. So we have x raised to 4 times y over x, and then we have e raised to a y square over x square. So we can now write x raised to 4, and this is a y over x, and e raised to a y over x whole square. So now this is a function of y over x. So we have x raised to 4 and f of y over x. So the degree of this function is 4. that is this function is a homogeneous function of degree 4. So now in the sixth example, we can write f of x comma y, and here we have x times y, right? So we can again multiply and divide by x. So we have x squared, then we have y over x, and then we have log of 1 plus y over x. So we have x square, and then we have y over x, and log of 1 plus y over x. Now this is a function of y over x, so we can now write x square and f of y over x. So this function is again a homogeneous function, and the degree is given by n is equal to 2. So now let us consider this last example. F of x comma y is equal to x raised to 1 over 3 plus y raised to 1 over 3, and here we have x raised to 1 over 4 plus y raised to 1 over 4. So let us take x raised to 1 over 3 common in the numerator. We have 1 plus y raised to 1 by 3 and x raised to 1 by 3, and here we can take x raised to 1 by 4 common in the denominator. So we have 1 plus y raised to 1 by 4 divided by x raised to 1 by 4. So we can now write x raised to 1 by 3 minus 1 over 4, taking x raised to 1 by 4 to the numerator, and using the laws of exponent, here we have 1 over 3 minus 1 over 4 as 4 minus 3 over 12, that is 1 over 12. And then we have 1 plus y over x raised to 1 by 3, and here we have 1 plus y over x raised to 1 by 4, right? So now here 1 over 3 minus 1 over 4 is equal to 1 over 12. Now this is a function of y over x, so we can write x raised to 1 over 12, and here we have f of y over x. So this is again a homogeneous function of degree 1 over 12. So we have n is equal to 1 over 12. Now let us consider the statement of Euler's theorem on homogeneous functions of two variables. Suppose we have a homogeneous function u, which is expressed as x raised to n, and here we have a function f of y over x, which we have just discussed with the help of the previous examples, and here u is x raised to n f of y over x. Then Euler's theorem says that x times the derivative, the partial derivative of u with respect to x plus y times the partial derivative of u with respect to y is equal to n times this homogeneous function u, right? So this is called Euler's theorem on homogeneous functions in two variables. We can also extend this theorem to more variables, but here we'll restrict ourselves to only two variables, x and y, right? So let us now consider some examples related to Euler's theorem. So here is the first problem where we are given u is equal to logarithm of x raised to 5 plus y raised to 5 divided by x plus y. Then we have to show that x times del u over del x plus y times del u over del y is equal to 4, right? So here what we will do, will first express this function like this. That is, if we take the exponential of both sides, we have e raised to u, and then we have e raised to log of x raised to 5 plus y raised to 5 divided by x plus y. So we can now write e raised to u is equal to simply x raised to 5 plus y raised to 5 divided by x plus y, because we know that e raised to a log of say a is equal to a, right? So now we have this relation. So let us take this function, that is e raised to u, as a g, right? Now let us show that this function is a homogeneous function of degree 4, as we have done in the previous examples. So let us take x raised to 5 common in the numerator. We have 1 plus y raised to 5 over x raised to 5. And here in the denominator, let us take x common. We have 1 plus y over x. Now here we have x raised to 1. This is x raised to 5. So we have x raised to 5 minus 1, and this function is a function of y over x. So here we have x raised to 4 and f of y over x. So we have expressed that g is equal to e raised to u, and that is equal to x raised to 4 and f of y over x. So our function is of this form, that is x raised to n f of y over x. So the degree of this function is given by n is equal to 4. So now we have shown that this function, that is g, is a homogeneous function of degree 4. Then by Euler's theorem, we can write this statement for our function g, right? So we have x times del g over del x plus y times del g over del y is equal to n times u. So our function is g, so we can write n times g, that is 4 times g, right? Now for g we can substitute e raised to u. So we have x times del over del x of e raised to u. Then we have y times del of del y, here we have e raised to u, and this is 4 times e raised to u. So substituting g is equal to e raised to u in this equation. Now the partial derivative of e raised to u with respect to x is given by e raised to u, and then we have del u over del x. So this is by chain rule, and again here we have e raised to u, and then we have del u over del y, and here we have 4 times e raised to u, right? So first we have differentiated e raised to u with respect to u. So we have e raised to u, and then u with respect to x. So we have del u over del x, and similarly here we have first differentiated e raised to u with respect to u, then we have e raised to u, and then u with respect to y. Now let us take e raised to u common. So we have x del u over del x plus y del u over del y, and here we have 4 times e raised to u. Now this e raised to u and e raised to u get cancelled, so we have the desired result, x del u over del x plus y del u over del y is equal to 4. So this is how we can prove this statement. So now consider this problem. So here we are given u is equal to sine inverse x square plus y square over x plus y, and we have to prove that x times del u over del x plus y times del u over del y is equal to tan of u, right? So for this what we will do, we'll take sine inverse to this side. So we have sine of u is equal to x square plus y square over x plus y, right? And let us take sine of u as a function g, right? Now let us show that this function is a homogeneous function of degree 1, right? So taking x square common in the numerator, we have 1 plus y square over x square, and taking x common in the denominator, we have 1 plus y over x. So here we have 1, so this is x raised to 2 minus 1, and then we have 1 plus y over x whole square, and here we have 1 plus y over x. And this is a function of y over x, and here x raised to 2 minus 1 is 1, so we have x, right? So this shows that our function g is a homogeneous function of degree 1, so we have n is equal to 1. So by Euler's theorem, we can now write x times del g over del x plus y times del g over del y is equal to n times g. So n is 1, so we have 1 times g, that is equal to simply g, right? So let us substitute g is equal to sine u in this equation. So we have x del over del x of sine u, then we have y times del over del y of sine u, and here we have for g we can write sine u. So now here let us differentiate first sine u with respect to u. So the derivative of sine is cosine, so we have cos of u, and then by chain rule we have del u over del x, and here we have cosine u, the derivative of sine u with respect to u, and then by chain rule we have del u over del y is equal to sine of u. Now taking cosine u common, we have cos of u, and then we have x del u over del x plus y times del u over del y is equal to sine u. Now taking this sine u, cosine u in the denominator of sine u, we have x del u over del x plus y times del u over del y is equal to sine u over cosine u, and sine u over cosine u is tan of u, right? So this is our desired result. So now let us consider this problem. Here we are given a function u is equal to logarithm of x minus y divided by root x plus root y, and we have to show that x times del u over del x plus y times del u over del y is equal to half, right? So let us raise these two terms to the power of u. So we can now write e raised to u is equal to e raised to a logarithm of x minus y over square root of x plus square root of y. And remember here the base of the logarithm is e, right? So we have e raised to u is equal to this term, that is x minus y over square root of x plus square root of y, because we know that e raised to a log of a is equal to a, right? So now we have to show that this function is a homogeneous function of degree half, right? So let us take e raised to u as a function, say g, and taking x common in the numerator, we have 1 minus y over x, and in the denominator let us take x raised to half common. So we have 1 plus y raised to half divided by x raised to half, and here we have x raised to 1. So using laws of exponents, we have x raised to 1 minus half, and here we have 1 minus y over x and 1 plus y over x raised to half, right? Now this is a function in y over x. So let us denote it by f of y over x, and here 1 minus half is x raised to half, right? So our function g, which is equal to e raised to u, is a homogeneous function of degree half, that is n is equal to half. So by Euler's theorem, we can now write x times del over del x of g. Here we have the function g, and then we have y times del g over del y is equal to n times u, right? So our function is g, so we have half times g. So now we can substitute the value of g as e raised to u. So we have x del over del x of e raised to u. Then we have y and del over del y of e raised to u, and here we have half e raised to u. So now let us differentiate e raised to u with respect to u. We can now write x e raised to u, and then by chain rule we have del u over del x. And here similar is the case with this term. First we differentiate e raised to u with respect to u. So we have e raised to u, and then del u over del y is equal to half e raised to u, right? Let us take e raised to u common. So we have x times del u over del x plus y times del u over del y is equal to half e raised to u. Now this e raised to u and e raised to u get cancelled, and we get this desired result, that is x del u over del x plus y del u over del y is equal to half. Now let us consider this problem where we are given a function z is equal to xy times f of y over x, and we have to show that x times del z over del x plus y times del z over del y is equal to 2 times z, right? So let us first rewrite this function z as x square y over x, right? And here we have f of y over x. So the purpose of multiplying this term by x and dividing by x is that this function takes the form that is f of y over x. So this expression is a function of y over x, and here if we cancel this x with this x, again we'll get the function z. So now we can write z is equal to x square times f of y over x, right? So where f of y over x is given by y over x, and here we have a small f of y over x. So now this is a homogeneous function of this form, where the value of n, that is the degree of the homogeneous function z, is given by 2, right? So now applying Euler's theorem, we can now write x times del z over del x plus y times del z over del y is equal to n times u, where our function u is z, right? And the value of n is 2, so we can now write 2 times z, and this is our desired result, right? So this result straight away follows from Euler's theorem by expressing this function z in the form that is x raised to n f of y over x, where the value of n is 2. Now consider one more problem. So here we are given a function u is equal to tan inverse y square over x square, and then we have to show that x del u over del x plus y times del u over del y is equal to 0, right? So this result also follows directly from Euler's theorem. And let us see how. We can take tan inverse to the left hand side. So we can now write this expression as tan of u is equal to y square over x square, right? And we can further write tan u is equal to y over x square, and which can further be written as x raised to 0. This is an important step, x raised to 0, because x raised to 0 is 1, and here we have y over x square, right? And this is of this form, that is x raised to 0 f of y over x, where f of y over x is given by y over x square. So this function is of this form, and we can see that if we take tan of u as g, then this function g is a homogeneous function of degree 0, right? So n is equal to 0. So from Euler's theorem, we can directly write for this function g as x times del g over del x plus y times del g over del y is equal to n times g, right? N times g, and n is 0, so we have 0 times g, that is equal to 0. So now taking g is equal to tan u, we can now write x del over del x of tan u, and here we have y times del over del y of tan u, and in the right hand side we have 0. So now differentiating tan u with respect to u, and then by chain rule we have x, here we have secant square u, the derivative of tan u with respect to u is secant square u, and then we have del u over del x plus y times, again differentiating tan u with respect to u, the derivative is secant square u, and then we have del u over del y is equal to 0. Now taking secant square u common, we have secant square u and x del u over del x plus y times del u over del y is equal to 0, and secant square u can be written as 1 over cos square u, and this is x times del u over del x plus y times del u over del y is equal to 0. Now multiplying this 0 with cos square u, here we'll get 0, so we have x del u over del x plus y del u over del y is equal to 0, because we have here 0 times cos square u, and that is equal to 0, and this is our desired result.